Hello, today we're going to talk about partial derivatives from section 14.3, and we have to learn what it means to take a derivative when we're using a multivariate function. So in single variable calculus, we could just say take the derivative, and once you know how to do that, it's not a big deal because it's usually y equals some function of x, and you're just taking the derivative with respect to x. The biggest thing that could throw you off is if the function was not y equals f of x, maybe it was like h is a function of t or something like that. So just different letters get thrown in. But now when we are told to take a derivative, so if you're told to take a derivative, you have to ask with respect to which variable. And on top of that, we also need new notation because before, if we were going to take a derivative, we would use d dx, and we would apply d dx, the derivative with respect to x, to the function of x, and then go ahead and take the derivative. Now, what we have to use is either this f sub x notation or this, and this is the way we say this one right here, is del f del x. And what it actually means, that little funny looking, almost like a backward 6, it actually means partial. So we're saying partial of f with respect to x. And we use the partial notation on the top and the bottom. And funny enough, even when I type this in, the code for it is \partial. So it's even like this is widely accepted notation to use. But we would read it as del f over del x, and it would be understood that it means you are taking the partial derivative of the overall function with respect to the one variable x. And if we are dealing with derivatives with respect to y, we would use f sub y or del f del y. Okay, so what is happening when we are taking a derivative, a partial derivative? So graphically, the del f del x is telling us the instantaneous rate of change of the function if we were to say, let y be a fixed value and then move parallel to the x-axis. So you're like moving in a specific direction along x, y is not changing. You know, if you're to like fix it at y equals 0 and just stay on the x-axis, walk along the x-axis, you're going to see how things change with respect to x and not with respect to y because you have fixed x, or you have fixed y. And similarly, del f del y tells us the instantaneous rate of change if we were to hold x fixed and then move parallel to the y-axis. So we can see this in some of the pictures here. In part A, it's saying, as we move in the positive x direction from the point 1, 1, negative 1, 1, so let's see where that is. That's right here. They've kind of labeled it here for us. And if we move in the positive x direction, we're on this, it's like a paraboloid, an upside down paraboloid or something like that. But we would be going up the hill if we were to move parallel to the x-axis from that point. And so then we could say that the del f del x of negative 1, 1 is positive because we'd be facing a direction in which we had to go up. And that would also mean that the function is increasing in that direction. Now, on this other one in part B, we have a point fixed. So we are at the point 2 with 3 halves. So out 2 by x and over by 3 halves on y. And if we were to try to move parallel to the positive y direction, we would be going this way. So I should maybe indicate that here. And so we would be going down the hill. And that would mean that the partial derivative with respect to, oh, it looks like there's a, it's funny, I've never noticed this before. There is a typo in here. This should say that del f del y of 2 with 3 halves is negative. For some reason, they accidentally put in del f del x. This is just a snippet from the book. Okay, so our partial derivative with respect to y, at that point, if we face in the positive y direction, we see we're going to go downhill, which means the change is negative, and f is decreasing from that point forward. Let me get my highlighter. Okay, so that's kind of a graphical interpretation of what's going on. All right, second partial derivatives get even more interesting because we have several ways in order to get them. In fact, for one two-dimensional, I should say, for one three-dimensional equation where we have, say, f of xy equals a function of x and y, we have 4 second partial derivatives. Okay, so here's the idea. If we were to take the partial with respect to x first, and I should highlight that with WRT just stands for with respect to, since we had to use it so much in here, I just wanted to give us a little acronym to use. So if we take the partial derivative with respect to x first, and then with respect to y, here's what that looks like. So this first notation right here, we've got f sub x in parentheses, and then the sub y is outside the parentheses. That indicates that the x derivative came first and the y derivative comes second, and then we see that order here in the f sub xy. Now, it's different when we use the Leibniz notation with the partials. So we would be taking del y of del f del x. So del f del x, that's the partial of our function with respect to x. Then we're going to take the partial with respect to y of that result. So that gives us del squared of f del y del x. Notice the order there. It's because the del y comes second and it acts on the left of our function and it stays there. We do not switch the order of the del y and the del x just because we want to. That is literally del y del x. And so the order is different in the different notations. Just notice that, and so that you're doing things yourself in the correct order. Now, if we were supposed to look at the partial with respect to y first, and then with respect to, it looks like I dropped an x. The way that's going to look is we'll have our partial with respect to y inside the parentheses. So that's telling me, first I took the partial derivative with respect to y. Outside the parentheses, it's saying, now let's take the partial derivative of that result with respect to x. And that's going to be written as f sub yx. The other way it could happen is, first, inside the parentheses, we have del f del y. So that's the derivative, the partial derivative of f with respect to y. Now we're going to apply the partial with respect to x on that function. And so it gets written as del squared f del x del y. Now again, notice the order that these things are written in. So depending on the notation you use, you're going to use a different order. And you need to be able to read both. You don't have to be able to use both, but I'm going to use both. So you need to be able to understand what I'm saying and the interpretation of it. Now, if I was to take the partial with respect to x both times, that would mean I've got f sub x on the inside of the parentheses, and on the outside I'm saying, now take the partial of your result. And so we would write it as f sub xx. Similarly, with the Leibniz notation, we have del f del x, and the inside and outside, we're going to take another derivative with respect to x. And that gets written as del squared f over del x squared. And it just means the second partial of f with respect to x both times. That's how you would read it. So second partial with respect to, second partial of f with respect to x twice. Whereas up above, this says second partial of f with respect to y first and x second. And the first one is saying second partial of f with respect to x first and y second. Okay, last one with respect to y both times, very similar to the previous one. We find the partial with respect to y, and then we find the partial of that with respect to y. And that would be written as f sub y. In Leibniz, we would find the partial derivative, del f del y first, and then we would take del y of that. And that would give us this result, del squared f del y squared, and it is read as the second partial of f with respect to y twice. Okay, so these first two right here are called mixed partials. And you have to know that, because you'll be asked to find the mixed partials, and you have to know that that's, oh, I have to find f sub xy and f sub yx. And what they tell us is how a partial in one direction is changing in the direction of the other variable, which is kind of weird to even look at. Sometimes what we'll do is we define z to be f of xy. And so in all of the above notation, you would just see z in place of f. So like del z, del x, del z, del y, z sub x, z sub y. Okay, so you have to be able to accept that z is f of xy. A similar thing would happen if we move to higher order partial derivatives, except that we would use w, and w would represent a function of x, y, and z. All right, let's see how we do this. In these first examples, we're being asked to find the first partial derivatives. So that means we want f sub x and we want f sub y. I'm going to use all my notations though. So f sub x, that's just equal to del f del x. And the way I write this is I'm going to take del x of x squared y squared plus y squared plus 2x cubed y. Now, if I'm taking the partial derivative with respect to x, that means y is fixed. That means I treat y like a constant, okay? If I treat y like a constant, then in this first term, if I take del x of x squared times y squared, the y squared is just a constant. So I focus on the x squared. The derivative of x squared is 2x. Times the y squared, that's still a constant that's hanging out there. So this gives me 2x y squared. Now, if I send the del x to the y squared, and I try to take the derivative with respect to x of y squared is a constant, and the derivative of a constant is 0. In the third term, I have a 2x cubed y. Again, treat the y like a constant, focus on the 2x cubed. So the derivative of 2x cubed is 6x squared, and the y is still there. It's just a multiplier. Okay, and then I would just simplify this by not writing the 0. So 2xy squared plus 6x squared y. That is f sub x, otherwise known as del f del x. Now f sub y is going to be del f del y. So we need to come up with our operator. It's del y. We're going to be taking del y of x squared y squared plus y squared plus 2x cubed y. And when we take this derivative on the first term, it's with respect to y, so x is now a constant. It is fixed. So we can kind of ignore the x squared, focus on the y squared. The derivative of y squared is 2y. So I get 2x squared y. The x squared stays there because it's a constant, okay? Now when I get to the y squared and I take del y of y squared, I get something. I get 2y. And then I move on, the del y of 2x cubed y, the 2x cubed is just a constant, and the derivative of y is 1, so I get plus 2x cubed, because the derivative of y is 1. And that's it. That's all I can do with that one. So those are the first partial derivatives of that function. Now let's see what happens when we introduce a few more items into this. So here we've got f of xy equals e raised to the x squared y. So now if I'm finding f sub x, I'm going to be taking del x of e to the x squared y. And I'm going to do it very carefully. So the derivative of an exponential is the exponential. And then there's a chain rule in there. So if I take del x of e to the x squared y, I get e to the x squared y times del x of x squared y. But the x squared is the only variable in here. Y is constant. So when I take the derivative of that inner piece, it's going to be 2xy. So I can rewrite this as e to the x squared y times 2xy, or 2xy e to the x squared y. F sub y is going to be del y of e to the x squared y. Same thing happens. The derivative of an exponential is the exponential, so I get the e to the x squared y times, and now chain rule, del y of x squared y. And in there, the x squared is treated as a constant. The y is my variable. So del y of x squared y is just x squared. So I get e to the x squared y times x squared, or I can write it as x squared e to the x squared y.